Hi everyone. So I'm sure you're excited to explore the FreeRTOS, like how to configure FreeRTOS kernel with ARM Cortex-M microcontroller. So basically, before we start the session, I want to show you something. You see this hardware setup here? You see there's a green LED and there's a red LED. So green LED is basically a green LED task and red LED will be a red LED task. So I'm going to demonstrate today how to create a task using FreeRTOS on Cortex-M microcontroller by porting FreeRTOS kernel with the STM32F446 microcontroller. And we will be creating two tasks, green LED task and red LED task, and then we will be blinking with different delays and task delay or something that we will use it. And I'm also going to show you live in the debugging how you can able to monitor the states of the task, right? And then if the time permits, then maybe probably we'll do some advanced stuff, right? So that's what I will be referring this hardware all the time in my presentation. So this is the end outcome. Apart from this, I'm also going to show you some of very interesting use cases, but this will be the base project that we want to use it. Okay, so now let's not waste the time. I hope you can see my screen. So how to configure FreeRTOS kernel in Cortex-M microcontroller? We will get started today with an overview, and then we will look at the FreeRTOS architecture in general, by the way. And then we will talk about the directory structure, like once we download the source file, what to do, how to organize the code. Then we would also talk about the list of FreeRTOS API and what that does and most of the generic and popular API, and then we will going to talk about the configuration file, that is a FreeRTOS config.h header file, which is very, very important and critical part of configuration of the FreeRTOS into your microcontroller project. Then we will look at how to create a task, so task creation process and some memory management. And then we will take an example where we will create and delete a task and then live debug and analyze the task states. That's what I said. And towards the end of the session, if the time permits, then we will take a question. Otherwise, we have amazing Discord server where you're feel free to drop your question. And there are a lot of great experts out there to help you. Okay, so this is the flow of our session today. So let's get into generic architecture. So if you know like RTOS, why we need and where the RTOS middleware goes. So we have, let's say, a microcontroller and some microprocessor. And then on the top of microcontroller and processor, we have a FreeRTOS API, right? So it's like a middleware that we use. And on the top of FreeRTOS, we will write an application code. That will be your firmware. You can also port it to your HAL API or something like that. And on the top of application, we basically write the user, the access of the user. So this is like generic architecture. If somebody have never ever have dealt with FreeRTOS and doesn't know where the middleware fit in, maybe this picture might help you where in the world of microcontroller and the processor, the FreeRTOS will go as a layer. And then let's just talk about the relationship between a task and the scheduler. I hope that you have seen my previous session. It was about interrupt, and we talked about multitasking a lot with using interrupt. But here we want to talk about a task and the scheduler for the multitasking using an RTOS. And the RTOS that we will be talking about is FreeRTOS. So let's say we have a microcontroller, and microcontroller has a CPU in it. So we have a CPU, you can see here, and probably you already know from the previous session that every microcontroller have at least a one CPU core. So if the controller has a one core, then it can only run one task at a time. So it can do one function at a time, right? But in the multitasking, if we want to achieve, then we probably need to run a multiple task. So you can see in the picture here, we have a multiple task here, right? So the CPU now have to execute a multiple task. Now, you might wonder what the hell this task is all about. I'm talking about task in a context of RTOS. Okay, so task is basically just a function, just like any other function. But the difference is here in the RTOS, the task is a function which has a dedicated memory, dedicated stack of its own, right? So that's the difference. So it's a function, has its own memory, has its own stack. So that's we call a task. So we have now a multiple task. Now, if the CPU, because CPU have only a single core and it has to choose which task to execute. For that, we have a real-time kernel that comes out of, let's say, a FreeRTOS, right? So we have a real-time operating system, FreeRTOS, and FreeRTOS has a scheduler. So look at this task selector. So task selector with a FreeRTOS scheduler will decide which task to execute, right? So CPU by this way can able to make a decision, okay, this task that I want to execute. And that depends on the priority. The third part is a priority. So because there will be some task has a higher priority and some task has a lower priority. So the scheduler make a decision of which task to execute. So that's how the multitasking is possible using a FreeRTOS into the Cortex-M microcontroller, at least for what we wanted to do. So what you get out of this slide is, one is a task. So we will be talking about a task, then there will be a scheduler, and there will be a priority. Okay, so this is the relation of a task with a scheduler to achieve a multitasking. All right, so let's just talk a little bit more about a multitasking in general. So what happens in multitasking is the CPU distribute the 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 CPU time distributed amongst the different tasks. So here in the multitasking, CPU time will be distributed across the different tasks, so the task will execute. So multitasking is done by scheduler in the RTOS kernel. That's what we seen in the previous slide. And then the tasks are scheduled for execution according to priority, because every task will have a priority. We talked earlier, like what's the difference between a task, when I said task is just a function with a dedicated stack, right? So here again, you have to notice that task also has one more feature, which is a priority, which the normal function doesn't have, right? Unless you give it or unless you code it. So that's how the multitasking is achieved. Now, even if you have a task and scheduler and everything, still the CPU needs to take care of these few parameters, right? So number of tasks that are responsible, then the resource requirement into the microcontroller, then the execution time, deadlines, and priority. These are few parameters which is responsible when we want to achieve the multitasking using FreeRTOS or RTOS in general, all right? And that's what we want to achieve. So what are the feature of FreeRTOS? Because we are very specifically talking about FreeRTOS right now. So what are the feature FreeRTOS has to offer us? So FreeRTOS provide us a preemptive and cooperative real-time kernel. So to achieve multitasking, to execute a multiple tasks parallelly into the FreeRTOS, we can able to use a scheduler, either preemptive scheduler or cooperative scheduler. So when you write the code as a developer, you can able to set whatever you want. So usually, very often we use a preemptive scheduler, not a cooperative scheduler. Now, you might ask a question, what's the difference between preemptive and cooperative scheduler? Maybe we're going to talk a little bit later this, but cooperative scheduler basically reduces the CPU time overhead, CPU overhead, but the preemptive is much more preferred because there's some drawback that the cooperative real-time kernel has. So preemptive scheduling that we can able to use along with the cooperative scheduling. Then the FreeRTOS is a scalable RTOS with a smaller footprint, so somewhere less than 10 kilobytes of ROM that you require. Also in FreeRTOS, they have a support for a tickless mode. So in case if you're working with a low power application, then you can use this tickless mode. You can enable tickless mode and then you can save a power consumption, right? That's how very often we discuss in office hours that how the FreeRTOS can able to help in the IoT products, right? Because in IoT product, if you have to run over batteries, then it's very important they have to consume less power. So you can use a tickless mode in FreeRTOS to optimize your application for low power. And then the synchronization and the inter-task communication is possible using a different feature that the FreeRTOS has to offer. So say, for example, message queue, you can use a binary and counting semaphore, you can use a mutex, event flag, you can use a task notification, or you can use a message and stream buffer. Now, I know you would say, okay, I don't know all these things, but don't worry, you don't have to know everything. I'm just saying these are the features that the FreeRTOS offer. And as we go along in the series, maybe in the future, we will have a lot of sessions coming up, and then you kind of have a dedicated session and could able to learn how to use this in your real project. Okay, so by this feature using, let's say, a semaphore, mutex, and task notification and message and stream buffer, we can able to achieve the inter-task communication in using a FreeRTOS. And then also we have a support in FreeRTOS for a software timer for task scheduling. So we have a software timer. Along with, we also have an execution trace functionality. So when the tasks execute into the microcontroller core, you can able to trace them. And I'm going to show you today with a live example, like how you debug, when you debug an RTOS application. We are not going into RTOS aware debugging, but of course this debugging will show you how you can trace the state of a task, which one is running and which one is ready state, and uh, the task has a state. So we're going to talk in the future slides, but I think now this is clear, like these are the features that FreeRTOS has to offer, and that's the reason why it's become a preferred choice for anybody who gets started off into the real-time operating system on the microcontroller or the processor. Now you might wonder, what is a requirement from the microcontroller if somebody wants to go with a FreeRTOS? So you need a core resources, and the core resources are, let's say, a system timer, which is a SysTick timer. We have had in the past a dedicated engineering hour where we talk about, my colleague talk about SysTick timer, how to use it. It's just like any other timer, but it's a dedicated timer in Cortex-M architecture, which is a 24-bit down counter. So you can use any other timer for RTOS, but it's good if you have a dedicated timer. And the ARM architecture, Cortex-M architecture, provide you that, and that makes your life very easy. So you need to have a system timer, SysTick timer. Then we must have a pend SV, which is a pended system call, which takes care of context switching, because when we switch the task, you basically switch the context. And then there is an SVC used to determine which OS service is requested. So whatever the OS service will get requested from the FreeRTOS or RTOS kernel, that will be served, right? So these are the core resources from the CPU you need. Now, you might then ask the question, what if, Umesh, I don't choose a microcontroller which is not an ARM? Because it's not about which microcontroller we choose. Even though today I'm using this STM32 microcontroller, you can port the FreeRTOS to any microcontroller, and any microcontroller could be an Atmel device or maybe a PIC architecture, AVR architecture, or something like that. In that case, what happens is you will have a very different sort of configuration file. We're going to talk about it, but the same FreeRTOS can be ported with the different architecture. Like you might have seen, like ESP32 has an express if architecture, but you still can port the FreeRTOS, right? So anyways, that's the core resources you need, at least for ARM Cortex-M architecture goes. The flash memory in your microcontroller, you need maybe somewhere around 5 to 10 kilobytes, not too much, right? You can, even if you take 80 mega 328 microcontroller, which has a 32 kilobytes of memory, so the memory is really smaller footprint, right? But when it comes to RAM, you need half a kilobyte, minimum half a kilobyte plus task stack, because we have seen when we create a task, every task has to have a dedicated stack memory allocated to it, correct? So if you port the FreeRTOS to any microcontroller which has a less RAM, then it's become a problem, right? So that's what I wanted to talk about. That many people then come and say, okay, there are libraries in Arduino where you can run FreeRTOS onto the 80 mega 328 microcontroller or something like that, but yes, there are libraries. Yes, there are port written by people. There are genius people online, but they can only do very little or few things. Maybe just you can create task here and there, a couple of tasks, and you can schedule the tasking. That's it, but not advanced stuff you can able to do. So now let's coming back to Cortex-M architecture. So these are the minimum system requirement you have to have if you want to port FreeRTOS to your microcontroller. And microcontroller could be anything. It could be from the TI or from Microchip or from ST or from any vendor. Okay, it doesn't matter, because FreeRTOS can be ported to any microcontroller. It's very popular real-time operating system. Now you might ask the next question, like, where can we download the FreeRTOS if I want to port to my microcontroller board? Okay, so you can visit freertos.org. That's the official web page. And if you click on the download button, then you will be presented with the download page, the dialog box, where you have two options. So you can select either FreeRTOS, the generic one, like 2022, that's the one that I use. And the another one you can get is 2024, which has written LTS. It's for long-term support, right? So probably you know that the FreeRTOS been acquired by AWS, and they do have a good engineer and forum support. So if you have any problem, you can reach out to them, get their support and all other things. And because it has a long-term support if you use that port, and it did had added so many libraries in there. So if you want to do advanced stuff like TCP stack or connect to AWS or maybe any other cloud service apart from AWS, you still can able to do that. Okay, so that's, but I just use a common port, which is a FreeRTOS 2022 version. Okay, so you just click on this download button and then you get the zip file downloaded on your computer. So once you download the zip file, then you can extract, and there will be a folder inside the folders and a couple of things. Now, remember one thing, whenever we talk about operating system, in our mind, we think like an OS image could be .image file or .iso file. That's how we have seen the Windows operating system, or maybe some kind of Linux version or flavor. Like when you download Raspbian operating system, you can download .img file, image file or something. But when you download FreeRTOS, they are just the source file. Okay, so they are just a C program. There are source files, some header files, and then people use this word called porting FreeRTOS, right? Porting means just taking the source file and adding into your microcontroller, right? And then you set up the path and everything in order to compile your project, right? That's what it means. I want you to make this clear, because when I was reading and researching and doing this for first time, I was a little bit confused about this old terms which people randomly use online. Okay, so you download the FreeRTOS online from their official web page, you extract, and then you see all the source file. That's what the FreeRTOS kernel is. It's just the C file written. Okay, all right, so let's talk about directory structure. You download, you extract, then you have a FreeRTOS folder, and what you find out inside the operating system, there will be a demo folder and there will be a source folder. So demo folder will have some template projects for different microcontroller like TI, for ST, for NRF, for all popular microcontrollers, right? And the source is the actual folder in which you will get to have a source code for a different FreeRTOS feature like task, queue, list.c, like these are the source file. Then there will be a portable folder in which we keep the file. Now, that means the FreeRTOS wants us to keep the file that are compiler specific. So let's say when I say I would today going to port FreeRTOS to my STM32 project in STM32 IDE. Now, because STM32 IDE uses GCC compiler, so the portable will be for GCC here in a compiler space, and then the platform will be an Cortex-M architecture from the ARM. It has nothing to do with ST, correct? So that's amazing. So that's why people use FreeRTOS or RTOS and operating system, because it's easy to port to other components or other parts, even if you move from part A to part B, right? So the porting between, I mean, with the source code become easier than the normal code. But I hope you get the point. This is how your directory will be structured when you port into your microcontroller project. All right, and then the platform and port C would become a part of the hardware abstraction layer. So you can write the HAL APIs and then you can access it from there, right? So the port will have and the architecture specific things in it. Okay, so the Cortex-M, I mean. So let's look at how your project look like when you port the FreeRTOS kernel in your project. Look at this in the left pan here, FreeRTOS project that's I have created here. And the entire project look the same like any generic STM32 project, except there is this FreeRTOS folder, right? And this FreeRTOS folder has the source folder. That's exactly what I've shown in the previous slide. That includes this include folder and portable folder, right? So include that some header files that has to do with the FreeRTOS features, like FreeRTOS offer us task, timer, queue, and other amazing feature to leverage in our application. And then there will be a portable, which include the port, which is an architecture specific Cortex-M, M4 in this case, in my microcontroller. One file is extremely important here, which we didn't talk about, is FreeRTOS Can you see this FreeRTOS This is a configuration file that the programmer, the developer has to write, because it basically doesn't come into the source folder. It's basically the developer has to write and then configure the FreeRTOS kernel. So it's very important. I mean, when you're learning the FreeRTOS and configuring FreeRTOS for first time, most of the time spent learning and doing stuff is in this folder, in this file FreeRTOS because where you configure your FreeRTOS kernel, right? And we're going to talk about it in detail. So this is how your project will look like. I will going to show you the actual live project, okay? Then we'll get into that everything step by step. I just wanted to take it into the flow, so make a sense in a logical sequence. Now let's just talk about the task creation process. When we create a task, I showed you a demo in the beginning where the red LED was blinking. So we want to create a red LED task, and in the memory you can able to see it has a dedicated stack and something new that you can see now, TCB, and you'll say, what the hell is this? So this TCB is a task control block, right? So whenever you create a task, it will be allocated a stack, and then you will have associated task control block. Now, if you wonder like what the task control block has, so task control block store the information related to task priority, and there will be an information about the local stack pointer, because it has to know where to start and where to stop. So the red LED task will create, then we will create a green LED task. It will have its dedicated stack and task control block, TCB. And this is how it looks into the memory when we create a task. Okay, now how much size you allocate to your task, that's a different story. We'll get into that when we looked at the FreeRTOS config.h header file. Okay, because that's the purpose of this file, is to configure all this parameter for your FreeRTOS kernel. So that's how you create a task, and that's how it takes the memory. Now let's just talk about, the top level task states. So when the task execute, the task run in the FreeRTOS into the microcontroller, your task either will be running or not running. This is just to keep things simple. Now, some people will come and say, okay, Umesh, there's no just running and not running. There are 4 states. There will be a running, ready, blocked, and suspended. There are 4 states. I know there are 4 states, but if we want to keep it simple in the beginning to learn, when we create a task, when we run the task, either the task is running or the task is not running. And that's how I wanted to simplify these things. So what does this mean when we say the task is running? So only one task can be run at a one time, because that's what we see. We are talking about a single core microcontroller, because right now the world is advancing so much that there are some microcontrollers which has a dual core microcontroller. It's just multiple core, right? So we are talking about a microcontroller which has a 1 core. So when the task is running in it, just one single task is running. And when we say not running, that means all tasks that are not currently running, not currently running and are in not running state. So they are not in run. So we can say that they are in ready states. So they are not running actually, but they are ready to run, but they are not running. The actual task which is running is the task that is running. I hope this makes sense. A little bit confusing, but to keep it simple, there's the task which is running and there's a task which is not running. And I'm going to show you live with an example. Don't worry, just wait and watch. So there is a running state and there is a not running state, right? So that's what I have just explained to you. So from the top, there are only 2 states that we want to focus today. And just remember, scheduler is the only entity that can switch a task in and out running states. This is what we are talking about when we are using a FreeRTOS or RTOS with the microcontroller, right? But by the way, you can also use interrupt with FreeRTOS. Maybe in the future we will have this advanced session where we will going to take this how to use interrupt in FreeRTOS and stuff like that. So now let's just talk about the configuration file. This file is very, very important because when you take the source code from the website and port into your microcontroller project, this is the file that you have to configure. FreeRTOS config.h. So FreeRTOS is configured by this header file, and this file is used to tailor the FreeRTOS to use a specific application. Let me just simplify these things. So if you modify this file, FreeRTOS config.h, it allows you to enable and disable a particular feature of the FreeRTOS. By enabling and disabling, you are basically customizing based on your application requirement. So you're not using whole thing that the FreeRTOS has given you. You are just saying, okay, let's say I need vtask delay function, so I can just enable that. So I can enable the macro into this FreeRTOS config.h header file. All right. Let's say I want to configure in my FreeRTOS kernel to use a preemptive scheduler. So I'm going to enable the macro for preemptive scheduler because I don't care for cooperative scheduler, right? So this is the way you can use this configuration file to configure your FreeRTOS kernel to use it and fit into your requirement, right? Isn't it amazing? Like this file is everything. If you understand this file properly, you understand basically most of the component of a FreeRTOS. Okay, let's go ahead. So let me just give you an example on this. Basically, I talk about it, but let me just repeat to put things in the perspective. So let's say I have in my project want to use a preemptive scheduler. So there is a macro into this config file. It's called config use preemption. If I enable this macro, so if I write the value 1 into this macro, then the preemptive scheduler will be enabled. And if I make the value of this macro become a 0, then automatically the cooperative scheduler will get selected, right? So that's how you customize it. I'm going to show you in a moment, but I hope this makes it clear. By now, all the time that you spend with me, you learn a couple of things. You learn task, you know now scheduler. There's one component task, scheduler, there's a priority, right? And there is a FreeRTOS config.h header file. You should know this 4 or 5 components. And now let's just talk about the hardware setup. So I have here the red LED connected to PA5 pin. So that's on the Nucleo board, it's a D13 pin. And the green LED that is connected to a PA6 pin. Okay, so it's basically a D12 pin on your STM32 Nucleo board. So green LED, we will going to use it for the green LED task, and red LED will be used for the red LED task, right? So whenever the task will execute, and when I show you the live hardware, then you can able to see like which task is running. So that's how we will going to use it. Okay, so let me just go to the source code and show you things live. Okay, so I hope you can see my screen. It's a STM32 Cube IDE, and here is the FreeRTOS project that I have created. And if you look at this project in the project pan, in the left pan, this looks like any other STM32 project, like Hell project. Nothing special. The special is just this FreeRTOS folder. And as we expand this FreeRTOS folder, you can able to see there is a source folder, and in a source folder we have this portable. In portable, look at this, there is a GCC compiler which I showed you in my slides, and if you expand, you have this architecture specific files, right? Cortex CM4, Cortex M4 with the floating point support, and you have the port.c and you have a port macro.c. All right, so this is all the GCC. And now let's talk about very, very important part, which is a memory management. So when you use a FreeRTOS, you have 4 different memory management schemes available to use. So there is heap 1, heap 2, heap 3, heap 4. And look at in my project, I'm using heap 4. So usually you might see a lot of projects and a lot of developer often use heap 4. I don't mean the other heap schemes, memory management schemes are not at all useful, but most of your purpose of writing an application code gets served by heap 4 memory scheme. Okay, that's why it's very common and generic one. But maybe in our Discord server, I would drop the link and then you can read documentation just to compare what it is. But now you get the point, like, because the task has to have a dedicated stack, right? And here all the magic happens, right? At least to do with the memory management. So that's how, this is what we call porting FreeRTOS to your microcontroller project. And then you can see the source file, like C routine, then event groups, list, queue, stream buffer, task, timer. These are the feature of the FreeRTOS that the FreeRTOS offer us to solve a multiple problem in order to, let's say you want to do inter-task communication, you want to do some advanced stuff, or use a queue to solve the mutual exclusion or something like that, a situation where you want to handle a critical data between a different task or something like that. So anyways, so these are the real core files from the FreeRTOS. Okay, we don't have to write any code at all. Okay, we have not yet written. This is all what we get when we download the code from the FreeRTOS. Okay, so this is the configuration file. Let me take you FreeRTOS config.h header file, and if I scroll down, you can see here we have written this config use preemption, and you can see I enable this by writing 1. So if I write the value 0, then this code, this project, my microcontroller project will use a cooperative scheduling. Okay, by putting 1, I'm saying that I want to use a preemptive scheduling in my project. Then another question comes, like if I use this STM32 nuclear board, like this one on camera, you can see. So this nuclear board usually runs on internal 16 megahertz clock, and we have to tell to our project that what clock it is running. And you can see there is a macro that says config CPU clock, which is a 16 megahertz. That's why we put a 16 million here. And then there's a lot of things, like here you put the memory, like what is the stack size, and then here's a heap size, and all other things, what is a tick rate, right? So 1000, and all those parameters you can just read and maybe learn, and maybe we'll get into that in the future. But I hope by now I proved the point, like you use this file, which is super important, FreeRTOS config.h, to configure your project parameters. I mean, to configure the FreeRTOS kernel, right? Now, let's go to main.c file. That's where we want to create a task, because I promised you to show you how to create a task. So this is a normal STM32 project. And you can see I added FreeRTOS.h header file. And this header file basically just added the FreeRTOS config.h header file in it, so we don't have to mention again. Okay, so adding this one line of code is good enough. And then because we are creating a task, we have to include this task.h header file. Okay, now if I scroll down, you can see there are two handles. Task handle is created, red LED task handle and green LED task handle. And I showed you there are two LEDs, and there will be a two task that we want to create, and one is for red LED and one is for green LED. Now let me scroll down and show you where the task is created. Look at this. Here is a red LED task function. And in this function, I'm saying I want to toggle the LED, which is where I have connected the red LED pin. So that's a PA5 pin, right? And look at this, I'm using hell delay function. Okay, now there is a popular API in FreeRTOS, vTask delay. So those people who are expert or have used FreeRTOS before and watching this session could able to say, oh, why won't you use this? This is where I wanted to show you. If I want to use vTask delay, means the delay function API of the FreeRTOS, then I have to first go to FreeRTOS config file, and then I have to enable this macro as one, right? If I do not enable this, then I'm telling to my kernel that I'm no longer interested to use this task delay function. And that's why I'm not using here a task delay function, right? But anyways, the other way is to show you that you can use a normal hell delay function as well. That's absolutely fine. They can go with the code. But anyways, so here toggle the red LED, and this task green LED task toggle the green LED that is connected to PA6 pin. Now we still have not created a task because the task has to be created here into the main function. So here's the main function where once you upload the code execution starts at the main function. And then here is the API that says X task create. Now this is the API that we use to create a task, and the task is red LED task. Now I always forgot to talk about this V. I'm not saying V red LED task because to pronounce it, it makes it super complex, but that's the naming convention of FreeRTOS. That FreeRTOS, I mean, the good practices and coding style is when the function return nothing. If it's a void function, then mention that it's the void function, right? By adding V in front of it. So red LED task, we want to execute, we want to create red LED task. We want to give it a name to the task as a red LED task. We want to give the size of a stack will be 128. And then the pointer null pointer, the priority that we want to assign is 1 because we are not doing anything special. And then we have to pass the red LED task handle. So that's how this line of code create the task named red LED task, which is have the memory size of 128, right? So that's the footprint. And similarly, we use X task create, and then we create a green LED task, and then we give the name. Again, it's the same thing. That's how we created a 2 task. Look at this one. Look at this hardware. So there are 2 LEDs blinking. Now you will say, okay, why this is blinking? We have not yet uploaded the code. That's okay. Keep a little bit of patience. So there are 2 tasks. Just assume that this LED is not blinking. Now, because there are 2 LED, 2 tasks. Now, in order to select the task to execute, you need to put this another, you have to use another API that's called vtask start scheduler. Remember the picture that I showed you. We have a task, the multiple task, and then we need a scheduler which select which task to execute. All right, so by starting the scheduler, now CPU can able to make a decision which task to execute, right? I mean, the scheduler basically decides which task to execute. And that depends on the priority. We keep both tasks as a priority 1. Okay, nothing special. So let me just show you the task running. So let me just click on the build button here on the top left corner. So let's see if there are any error or warning. Okay, so 0 error, 0 warning. And let me just click on this debug icon in top menu bar. Okay, so we are into the debug mode, and for you to confirm, look at this, the both LED is off, right? You can see the both LED is off. Now, if I click on this resume button, look at this, when I click on resume button, you see the both task starts executing, and they are blinking now with 500 milliseconds, exactly what we wrote into when we created a task. So let me suspend the task. Okay, the moment I suspend the task, I want to show you something interesting. So let's go to Windows, Show View, and FreeRTOS. If somebody have never ever debugged the FreeRTOS, then go to FreeRTOS task list. So click on it, and now you see there are some information here, and it says the green LED task. Look at this icon here, this arrow that says the green LED task is running, and the red LED task is ready. So it's not running. So actually the green LED task is running according to this debug, and the red LED task is ready. It's yet to run. So let me just resume again. Look at this. When I click on the resume button on the top menu bar, so execution would start again. So LED is blinking. Let me suspend again. Now look at this. The arrow has moved down to the red LED task. Can you see? Now it says the green LED task is running and red LED task is ready. Isn't it amazing? Like you can even see here some parameters like variables in case if you want like delay and the other. That's not very important, but you can able to see in the task uh, FreeRTOS task list which state the task are. Now I understand that this information is not good enough. That's why in the future engineering hour episode we are planning to bring some advanced session where we will going to show you how to use a trace analyzer and literally measure the timing between the task execution, right? So you can literally measure with one shot or continuous capture. You can capture the task and then you can analyze the data and stuff like that. But this is good enough for somebody who have not yet done anything with FreeRTOS. Okay, so that's how you create a task and then you debug the task. Let me just terminate the debug session. And I think now you know how to create a basic FreeRTOS project, which allow you to create a task. All right. Now let me just close this project. I have something interesting to show you. And then I want to take you to another project. So maybe this one we can take create FreeRTOS task. Let me open. These are like few code that I wrote just to show you the capability. So let me go to main.c file. So here again, look at this. I'm using the same FreeRTOS.h header file. There's a task.h header file. And in this case, I have created, in this project, I have created only one single task. And I named it very lazy name, my task one. It doesn't matter what you name it. So then I created this task one. So X task create my task one. So I named it as a task one. I have given a stack size of 200 and then null pointer. And then the priority is basically 0 here. Like you can use this macros as you get develop expertise. You kind of know that you don't need to write always hard coded numbers, right? There are a lot of macros. It's very mature. FreeRTOS is very mature operating system. Like you have everything in place there. Okay, so some code will be written for educational purpose, so they are like that, but the priority is 0, and then this is my task one handle. So just a single task. Now let me talk the important thing. What the hell this task does? So look at this task one, my task one function. So this function basically what it does, it has a count variable, and this count variable will keep incrementing by 1. And look at this here, I'm using v task delay function. All right, and I'm putting 1000 here. All right, and now let me take you to FreeRTOS config.h header file. Okay, and if I scroll down, you can see I enable this macro include v task delay 1. Correct? So if this would have been 0, then it would show me error while building the source code, right? It has to 1 enable it. Because we enable this macro, now when we build the code, look at this, when I build the code, all right, look at this, 0 error and 0 warning. And let me debug this code as well. So let's click on debug button. And if somebody doesn't know how to use a serial wire viewer for debugging, because I'm using it for this project, then please check out a video that we have done in January or February, I guess, this year. So we have already a video. Maybe Brandon will put the link in the chat box. So once we are in a debug session, then I want to take show view, serial wire viewer, and then look at the serial wire viewer data console, ITM data console, right? So look at this ITM data console. So let me start capturing the trace. And then let me click on resume, and according to the code that we have wrote, it will print the count value. It's not printing the count value, right? So let me reset, press the reset button. It still doesn't work. It's happened sometimes. Just suspend the code. Okay, just suspend. Click this button again because I'm not using mouse here. I don't have any USB port anymore to my laptop. And now I resume again. And now you can see it starts printing hello world like 4, 5, 6. Let me press reset button. If you don't trust me, it starts printing from 0, 1, 2, 3, 4 because the task 1 is executing. Okay, and task 1 is incrementing the count variable by 1 every 1 second, right? So we learn how to create a task by using X task create function. Then we learn how to use X task delay function, right? And now let me show you how the task can delete the task, right? So in the task itself, we will delete the task. Let me show you the magic. Let me stop this execution. And let me quickly close this project. And I have a special project for you. Create and delete task. We are running out of time. I know this. And let me quickly get you to the main.c file. Again, I have the same function written here. It's just a myTask1 function, right? The only magic happening in the code is, look at this. It starts counting this count variable. It will start incrementing. And here I'm saying if the value of the count variable matches to 5, then I'm going to use vtask delay function. This is in FreeRTOS API that can delete the task. And the task that I want to delete is associated with the task1 handle, right? So when I write this code, then what happens is the count variable will increment till only 5. And once the count will reach to 5, the task 1 will delete the task 1 itself. Okay, amazing, right? So let me just build the code and quickly debug and show you. So the task can release the memory, right, itself. Amazing. So if you don't use FreeRTOS and real-time operating system, you can't have this kind of features, right? So let me click on debug button and it would take us to the debug mode. I hope this will happen quickly. We are in the debug mode and here is SWV ITM data console. That's where we see the debug output. And by the way, if you know the ITM console, we have to enable this port 0. Let me just go back again and click this red button, start trace, start capture trace, and then click on resume to start executing into the microcontroller. And once it executes, then it's, let me just suspend. Again, this happens for some reason, the scalability mode. Let me 2-time click. And now let me resume the task. Execution doesn't. Let me suspend. Or maybe this time I can just terminate and rebuild again. Oh, by the way, if you go to FreeRTOS config.h header file into this project, and let me quickly show you. vtask delay macro we have enabled to 1, right? So if this macro is not enabled, we can't use this API. So let me build it again. And then click on debug. I hope there shouldn't be any loose connection between the debugger. All right, so we then can go back to SWV traces. It was there, by the way. And then start trace, resume. Now you see it's working, right? So it starts executing, the count variable start incrementing 0, 1, 2, 3, 4, and the 5 didn't get printed, right? Because the condition made what we wrote into the if statement. So as soon as it hits to the count variable hits to number 5, the task 1 delete itself and nothing happens, right? So let me press the reset button again, see what happens. When I press the reset button, it again starts executing. It will count, and when the count variable reaches to number 5, then it will delete itself, right? So we created a task. I have shown you how to use the vtask delay function, and then I also have showed you how you can delete your task, right? I hope this is good enough for just the beginning to use the FreeRTOS API ports, right? It has amazing documentation and everything is great for FreeRTOS. And feel free to come to this Discord server and discuss with us. So let me take back to the presentation. The presentation is gone. So this is what we've seen for the setup. And yeah, thank you very much for being a part of this DevHits community.